Well, thank you very much for letting me speak at this great event and accepting the virtual presentation. I'm going to talk about how to enable safe self-driving cars by using monitors. And I think in comparison to the previous talk, this is on a much, much higher level where I'm discussing more principal questions. So I've structured my talk in three parts. I'll first talk about a very simplified view of an automated driving system. And I will explain that it's prone to errors, and if we don't handle these errors or failures, I should say, then critical things may happen, incidents that may lead even to lethal consequences. As a consequence, we are going then to look into what can we do about that, how can we handle failures, and I will look into two fail operational design principles, namely TMR and the do-a-checker approach. So the do-a-checker approach is also sometimes called as a command and monitor approach, depending on which industry you're talking to. So I'll call it a monitor. If you're more familiar with do-a-checker, so the monitor is almost equal as a checker in this terminology. So I'll talk about the monitor and specific design aspects of the monitor in the third and final part of my talk. So let's start with a very, very simplistic view of an automated driving system. And what we see here is we have sensors, we have the automated driving system itself, and we have actuators. So as I guess it's very natural to understand that sensors perceive the world. Typical sensors would be camera systems, LiDAR systems, or radar systems. So anything that makes you able to get a sense of how the world operates and what the world is. Those sensors feed into this big block of automated driving, where we have the typical tasks of identifying objects, making a plan, calculating trajectories. And if you're fine and done with the trajectory planning, you output or you generate control commands towards your actuators, such that your car will move along the calculated trajectory. So I've depicted again a very simple scenario on the left of this slide. So it's simply a car driving on a street with 3 lanes, and somewhere in the future ahead of the car there is a rock blocking the street. So if everything of the simple driving system works as specified, works as expected, then there is no issue, because we've designed the car in a way that it will safely identify a way, a trajectory around the rock and keep safety of the driver and the car established. But we are not living in a perfect world, and all of these little boxes and circles I've depicted here, the sensors, the actuators, and in particular the automated driving systems by itself, they are prone to errors. And so what might happen is, if you don't design the system carefully, that a failure in such a system may result that the car will not calculate a safe trajectory around the obstacle, but rather will cause an incident, in this case a crash, into the rock. So the question is, how can we design a self-driving car and automated driving system now sufficiently reliable and sufficiently safe that even those kind of failures in the system can be tolerated? And this is not a trivial problem, as I guess you have also understood from the previous talk that was very detailed in how failures in the clock synchronization aspect of the system can be handled. But even if you look at this very high level of system view, where we have a sensor, automated driving system, and actuators, the simple replication of the automated driving systems for the sake of fault tolerance will not work as easy. And one of the core reasons for that is that you design even replicated automated driving systems. They both may operate correctly. They both may return safe trajectories. But the problem is, since they are not, in most cases, designed exactly the same, they will most likely result in trajectories that are not identical. So the car has to live with the situation that the replicated automated driving systems generate safe trajectories, but the trajectories they generate, even though they are safe, will not be identical. We call this problem replica non-determinism in the literature. And it is a real problem because you could say, well, if both trajectories are safe, then I can pick any of the two. But that's obviously not a good strategy, because indeed one of the automated driving systems could have a failure. So the car doesn't know whether it is in a situation where the two different trajectories are both safe, or if one of the two trajectories is safe and the other one is faulty. So if your strategy was to pick just any of the two trajectories, you may just pick the faulty trajectory that of course then would result in the crash as depicted here on the left. So the aerospace industry and space industry have been named just before, and they actually deal with this kind of problem since, I don't know, probably 60 years. And two very paramount design choices or the design paradigms that are known from these industries are TMR, triple modular redundancy, and the check and monitor approach, which I'll come to in the next slide. But let's start with the TMR approach. TMR simply means that you replicate your system, and for the sake of simplicity, let's assume that the system that we want to replicate and that we want to protect is the automated driving system itself. So this big blue block that we had on the previous slide in the middle. So let's assume that this can fail as a whole. We say this is a fault containment region, and now what we do is we replicate this system 3 times. So this is essentially depicted here on the right of the slide. And you have a voter that will take the outputs of the fault containment regions and decide if 2 of the trajectories are consistent, 2 of the trajectories are kind of the same. It will result, or it will use or propose this trajectory to use for the car. But then, as we have just seen on the previous slides, there is a big issue. And the big issue is that replica non-determinism causes that even though the fault containment regions may be operating correctly, like let's say fault containment region 1 and 3, the output may differ. So as you see again, the trajectory 1 and trajectory 3, they are still safe. Only trajectory 2 is unsafe. So the task of the voter becomes very complex, because now the voter cannot simply take 2 trajectories and make a bitwise comparison and see if there are any 2 trajectories that are the same, but it has to be much more sophisticated. So you may argue now that, well, but certainly I can do something, I can coordinate the FCRs, the replicas with each other such that it makes the life of the voter more easy. And yes, that's true. Of course, you can do something that we sometimes call congruency exchange. You allow the information exchange between the fault containment regions. But the problem that you have is that this comes at a price. And the price or the cost of this coupling of the independent FCRs comes at the cost of design diversity and independence. So if you couple those FCRs, if you allow exchange of information, you need to be very, very careful about not stumbling into common cause failures. Meaning that if one of the FCRs becomes faulty because of the coupling, also the other FCRs that are coupled to this FCR become faulty as well. So you have a design trade-off. The design trade-off in TMR is between the independence of the FCRs and the consistency of the outputs to make the operation of the voter easier. The second design paradigm I'm talking about is the command and monitor approach, or as I said, that's equal to the do-a-checker approach that you also find as name for this principle. Here again, we replicate our components, but we do the replication in a different way. So you see again here on the right, multiple fault containment regions, but the big difference in comparison to the TMR is that in this case, the FCR1 operates as the commander or the doer in the other terminology and produces a trajectory. And we have a second fault containment region, which is acting as a monitor. So instead of producing another trajectory, the monitoring FCR observes and checks the output of the first FCR. So it's essentially what you see here in this box, the FCR2B check. So instead of having a second FCR producing another trajectory and voting, like in the FCR, in the TMR approach. In the commander monitor approach, you have a commander that produces trajectories and a monitor that checks whether the trajectory is safe. So what do we do if the check is indicating that the trajectory produced from the commander is faulty? Well, in this case, we'll hand over to a backup system, which again is a very similar strategy as was proposed by the previous speaker. However, you still have a trade-off between conflicting requirements that's very similar to the trade-off that you had at TMR. But here the trade-off in the common approach is between the independence of the designs of the commander and the monitor and the false positive or false negative detections of the monitor. However, we believe that the commander monitor with fallback is well suited as architecture for safe self-driving cars. And this is mostly for two reasons. The first one is that you are able to avoid this complexity in the voter to understand when two distinct trajectories are the same or are equal. And the second point is that having this structure of a monitor and a commander in place, it's very easy now to, we hope that it's easy to collaborate in an industry-wide consortium and standardization activities to actually nail down what the safety checks should be that need to be implemented in a monitor. So I think this approach actually makes collaboration between different parties in the whole industry much easier. So here is a very quick simulation of what I mean with a monitor. I'll rather go quickly through that due to the sake of the timing. But you see on the left a simulation. You see an ego vehicle that's driving on a road. Here in the middle, you see the world model of the monitor. So the world model is essentially the white space, which indicates a free space to travel. And you see in green the trajectory that is proposed by the primary, by the commander or the doer. Pick the terminology as you like. So here on the right, we have two checks that the monitor imposes on this trajectory. And they are, I guess, also easy to see. So the one check is whether the trajectory that's proposed by the commander is indeed sufficiently in the white space. And if it's not, then this exceeds a certain threshold. And the monitor indicates that the trajectory from the commander is faulty. And the second check is simply an indication of whether the curvature of the trajectory is in safe margins, or it would cause otherwise the car to become unstable. So if you just execute that, you'll see that at some points we start to move the green trajectory. So this is a fault. We simulate a faulty commander that would result in steering the car into the car on the left. And you see that the monitor, by executing this check, it checks whether the trajectory is in the white space, indicates that this is a faulty trajectory, and it would fail over to the fallback. So I'll just keep the simulation for a couple of seconds longer because you'll see also a vehicle dynamics risk. So here we have an example where we again inserted a fault in the commander. It became faulty. But in this case, since there is no object on the left lane, it would actually be safe to drive along this trajectory. So just a couple more seconds. And we should be almost completed. So now it goes into a curve, and you see that the trajectory aims the car to oversteer, and this would cause potentially that the car becomes unstable. So the monitor classifies the trajectory proposed by the commander as faulty. And again, the system is switched over to a backup system. So with that, I would like to stop this animation and move forward with discussing concrete design aspects of such a monitor, or in general problems that we face when we want to construct such a monitor. And this is the third and final part of my presentation. First of all, one of the big challenges that we face in autonomous driving is the use of machine learning techniques and technologies. And I guess as you are aware, there is no established procedure on how to guarantee the safety of such technologies. So there is no assurance process that you could follow that guarantees you that your machine learning based system will give you a reliability of 10 to the, I don't know, -6, -7 failure rate. So what do we do about it? Well, I think we can look at this problem from an operational design domain perspective, because there is a hope that with the first applications of automated driving systems being on the highway, that the operational driving domain is simple enough that we can construct a safety monitor that operates without machine learning techniques. So what I'm saying is that for the safety critical monitor that monitors the output of the commander, there might be a chance that we construct any form of sensor and sensor fusion techniques that will come without, that's possible to operate without machine learning techniques. But then that's just the first step. Yeah? So we, of course, have as ultimate goal to operate safe self-driving cars, even in urban or city-like environments. And then certainly the ODDs at some point become so complex that it's rather unlikely that we'll come to a point where we can use a monitor without machine learning techniques. So, but then I would say the prime design principle for the monitor should be that we should strive for design of a monitor that minimizes the use of machine learning techniques as much as possible. So yes, for example, for object recognition or object detection in a very complex scenario, you might have to use machine learning techniques, but probably you don't need the machine learning technique for generating an appropriate and safe trajectory. So the first issue and design principle for a safety monitor I would impose is how can we minimize machine learning for such monitors. The second issue with monitors is actually a complete system-wide question is, what is the safe and sufficient set of sensors that the whole system needs to implement? And if you follow the news, you very much likely have heard that some manufacturers believe that you can construct safe self-driving cars with camera systems only. I would say the majority of car manufacturers that we talk to has actually more the vision that whatever diversity in sensor techniques you can use, you probably put it on the car to really make it safe. So typically, in order to make it safe, the argument goes, you need camera-based systems together with LiDAR and radar techniques or radar sensors. So it's quite typically a mix of those sensors that we see that car manufacturers look into. So but even if we agreed on a diverse set of sensors and a number of sensors, what's now still a problem to be answered is how are these sensors distributed in terms of the fault containment regions. So there are two extremes. The one extreme is that each individual fault containment region has its own set of sensors. And the other extreme is that all the sensors are fed into all the FCRs. And then there is, of course, hopefully some sweet spots in between those two extremes. I think what should come very natural and clear is that if there is a decision that a sensor is reused between independent FCRs, between replicated automated driving systems, there is of course now a risk that this shared sensor could cause a common cause failure again in these independent FCRs. Or in other words, the independence of the FCRs is limited again. So it must be proven that a failure of a shared sensor, like any other shared input into the FCRs, into multiple FCRs, cannot cause a common cause failure. And I should say that the distinction between having individual sensors for each box versus having shared sensors, it's not just an economic question. It's not just saying that well, if I had all the money in the world, it's the safest thing to do to get every box, every FCR, its independent sensor data. I think there is a more theoretical problem to be discussed as well. The third issue that you already discussed a little bit in the previous part is that the issue that whether you allow information exchange between the FCRs or not. So both in the TMR as well as in the common approach, we have independent fault containment regions. And the question that arises is how much information exchange do we allow between those? And we have discussed in the TMR, the problem if you limit that is that the voter has a very hard time to understand if two trajectories are the same. And we have discussed that in the common approach, this lack of coupling between FCRs could lead to a high number of false positives or false negatives. So I pose this as another very challenging and interesting research question. How much information exchange is there permissible and allowable between independent FCRs? And I should say that in the literature, this is actually a question that now becomes quite prominent. So there is a recent paper from John Rushby that argues that all the FCRs should share the same world model. And we have another paper from Hermann Koppetz that argues that those models should be completely isolated. And then we pose some sort of a compromise saying that there should be or could be a limited form of coupling information flow. So it's a very interesting discussion item and research question right now, also in the research community. So I've captured also a couple of other research challenges in monitor design. I've summarized those challenges here on this paper, on this page. There is a paper together with this presentation that if you're interested in, just drop me an email and I'm more than happy to share that. The additional design aspects that I'm depicting here is on the one hand, ASIL decomposition. And again, we've targeted that in the previous talk. So the big problem is what ASIL levels, what ASIL targets do we have to reach for each of the FCRs, and probably inside each FCR, I can do again an ASIL decomposition. So what the right way to go there is one of the big challenges to bring these systems on the road. On the top level of FCRs, it could even be the case that, let's say, since you have a monitor with a very high ASIL, you could potentially trade that for a rather low ASIL on the commander side. I've talked already about design diversity, but I think it should be clear here that design diversity cannot simply and by itself be achieved by a car manufacturer going out to 3 different suppliers and ask them to implement 3 different FCRs. Because the techniques and the methods that these independent suppliers might choose will be or have a high likelihood to be the same or at least be very similar. So when we talk about design diversity of the different FCRs, actually some form of control would have to be imposed in quite narrowly steering which algorithms, which techniques are used, permissible in which FCR, such that you avoid multiple FCRs using the same procedure and therefore again raising an issue of a common cause failure. The command and monitor approach, I believe, is also a vital and very important step into an advanced verification and validation strategy, because the hope would be that the monitor has a development cycle that's rather low compared to the development cycle of the commander. Or in other words, once you've established your safety monitor, hopefully the safety monitor doesn't have to be updated as frequent as you are allowed now to update the commander. And in the commander portion, you're then able to leverage all the cutting edge technologies that come out of new industries. I also discussed standardization already, and I truly believe that making the safety spec a subject of collaboration is the only way forward. So I think we need to have very clear rules and guidelines and written down in text. What are the safety checks that such a monitor has to conduct, such that we can guarantee that the output of the commander is safe. And there are already many standardization collaboration activities. Some of them are listed here, the UL 4600, the ISO 4804, and the autonomous initiative. So with that, I already conclude my talk.
So thank you very much. That's really interesting. As usual, you get a few answers and even more questions. And while you're preparing your questions, I can start with a little one. And this is perhaps related to the debate between the Professor Rushby and Kopets here. Because it's about what we mean by a fault containment region in this context. To my understanding, the fault containment region is not an absolute property, but a property of the faults that you constrain by the safety requirements on that part of the architecture. And for me, having been inside this for a number of years, I don't have a stable understanding of the granularity when you apply this kind of redundancy patterns. So my question to you, Wilfried, right now is, do you think that we are having a rather understanding where to apply this kind of monitors, this kind of redundancy patterns with respect to some failures? Or is that because the granularity of how, I think we should go much further down in granularity than what you depict right now. I understand by pedagogical question, you show monitors on quite high level questions, or do you think, where is the future here?
No, I think from my perspective, it's rather clear. It's on the top level, yeah? So you could even say that each of the FCR might be even an ECU. And I think that's the way you should approach the problem, because any form of merging then these FCRs into single ECUs is simply a matter of efficiency and cost efficiency in particular. But in the principal architecture choice, you should start with assuming that each of the FCR is an ECU by itself.
Okay, very interesting question. I think we will look forward into this in the future. So please hear questions from the floor.
Thank you for your presentation. One question concerning using this doer checker principle for the perception stack. What we experienced is that when using a multimodal perception setup, you end up in situations where the doer checker roles quite frequently, let's say, interchange. You cannot rely on the commander being the commander for your complete ODD definition, but due to the systematic strengths and weaknesses of the sensors as such, these roles seem to interchange. Do you have a view on that?
No, I don't think that the roles should interchange. Yeah. So if you have a system architecture where that happens, I'm not sure whether that's the right system architecture. So if you're saying that because the sensors are diverse and therefore sometimes the doer is the doer and sometimes the doer is the checker and the other way around, I'm not sure whether this is a sustainable architecture for a safe autonomous car.
Unfortunately, it's the physics behind that. Specific sensors have very specific strengths and
yes,
weaknesses.
But the question is, why don't you use all the sensors all together for the commander, and if necessary, a redundant set of exactly those sensors also for the monitor? And that's the question that I posed here as, I think, the second challenge. Yeah? So it's really a question whether you can keep this cost down in saying, okay, I just have 3 sensors, and by selecting the the fault containment region to which I feed those sensors, I can solve this issue. I think really that has to be questioned, whether you can do that or whether you really have to have also redundancy in the sensors.
Okay, thank you.
So next question, please.
Thank you again for your interesting speech. My question is related to the role of the monitor with respect to availability. Could you give an comment on it, how you would require, or what level of reliability would you require for the monitor not to have a too strong effect on the availability of the total system? For safety, I think its solution is very good.
Oh, thank you, thank you. No, I think that that's a very good question, yeah, and of course there is a big issue, yeah. And it ties also to the third larger topic, how much you allow the coupling between the monitor and the commander. But yeah, you are quite right. I mean, if the monitor is very coarse and it classifies trajectories, even though they are safe from the commander side and objectively safe, if it qualifies this trajectory as unsafe, you have safety achieved, but you might have an unacceptable level of availability. So there are strategies to mitigate that. One strategy is to allow information exchange between the commander and the monitor. So the monitor could actually provide the world model, its own world model, to the commander and say or ask the commander to only return trajectories that satisfy the world model of the commander as well as the world model of the monitor. And by doing so, you would have eliminated any form of systematic false negatives from the monitor. The issue with this architecture to a checker, if the monitor interferes too often, is of course that it will leave or that you put a high burden on the fallback system. Because if you say, well, I don't care because the monitor can intercept the trajectories very frequent, that doesn't matter so much because I have a fallback system. I think that's also critical because now you put the fallback system into a position where you have to have probably an ACLD system there as well. And the question is, okay, how do you achieve that? So there are challenging questions. I think you bring it exactly to the point. What I presented here is simply on the top level view. And now it's, I think, in the challenge is to construct those elements in a way that the numbers together give you the desired safety and reliability.
Any last question? Otherwise, I propose we thank the speaker again. Thank you so much.
Thank you.